Hey everyone, and welcome to this explainer. I am absolutely pumped to have you here today because, well, we are embarking on a truly epic geological adventure. We're going to track the incredible journey of magma, starting way down in the fiery, pressurized depths of the Earth's interior, all the way up to the surface, where it dramatically erupts and, literally, reshapes the world we live in. It's a story of immense, unstoppable power, terrifying destruction, and, surprisingly, vital creation.
So here is our flight path for today. First, anatomy of an eruption. Second, a tale of two lavas. Third, classifying the fire mountains. Fourth, landforms inside and out. Fifth, where volcanoes call home. And finally, effects, destruction, and creation. Let's dive right in.
Starting off with Section 1, Anatomy of an Eruption. Before we look at the massive mountains themselves, we've got to understand the basic mechanisms under the hood. At its core, you have to think of a volcano less like a giant mountain and more like a planetary doorway. Better yet, picture the Earth's interior as this highly pressurized, superheated pressure cooker. A volcano is essentially the vent, the opening, through which all those intense heated materials forcefully escape. We're talking about a completely volatile mix of water, rapidly expanding gases, liquid lava, and solid rock fragments just violently pushing their way up to the surface. Now, what's really fascinating is that this entire process, which geologists call volcanicity, is actually a two-part play. Act 1 is the endogenic mechanism. This happens completely out of sight, deep down within the crust and mantle, where rock melts to create that hot, liquid magma. Act 2 is the exogenic mechanism. This is the dramatic stuff we see on the news. It's the exogenic appearance of that hot liquid magma erupting right onto the surface, which is exactly when we start calling it lava. Moving right along to Section 2, a tale of two lavas. Because, here's a little secret of geology, not all magma is created equal. It all comes down to chemistry. A volcano's entire personality is dictated by one main thing, its silica content. On one side of the ring, we have basic lava. This stuff is the hottest, it's packed with iron and magnesium, but it is very poor in silica. Because it lacks that silica, it's highly fluid. It just flows out quietly, spreading over massive areas and creating these incredibly wide, flattened shield volcanoes. Now contrast that with acidic lava. Acidic lava is absolutely loaded with silica, which makes it incredibly thick, sticky, and viscous. Because it's so gooey, gases get trapped inside. The pressure just builds and builds until, boom, it erupts with a loud, violent explosion, throwing out massive volcanic bombs and building steep-sided domes. Which brings us to Section 3, classifying the fire mountains. Knowing that these lavas behave so differently, how do we actually categorize these volatile forces of nature? Well, connecting right back to our lavas, we get two distinct styles of eruption. Acidic lava gives us the violent or explosive type. These are rapid, heavily destructive events. Think of those sudden, devastating blasts that literally blow the tops off mountains. On the flip side, that highly fluid basic lava gives us the effusive or fissure type. These are much slower, quieter eruptions. They often just seep out along massive fractures or faults in the earth, slowly repaving the landscape over time. But beyond just how they erupt, we also classify them by their life cycle, or their periodicity. First, we have our active volcanoes. These are the ones erupting frequently, famous examples being Mount Etna and Stromboli. Then we have the sleeping giants, dormant volcanoes. These have erupted in the past and still show geological signs that they're going to wake up again. Mount Vesuvius is a prime example of this. Finally, we have extinct volcanoes, like Shiprock, which have absolutely no recorded historic eruptions. But I'll let you in on a chilling geological fact. Because the Earth's timescale is just so vast, it's almost impossible to be 100% sure that a volcano is permanently extinct. All right, let's head into Section 4, landforms, inside and out. When magma and lava finally cool down, they leave behind some magnificent geological footprints. Let's start above ground with extrusive landforms. If you have viscous lava that solidifies really quickly right as it exits the vent, it piles up into steep ash or cinder cones. If the volcano takes turns, say spewing lava one century and blasting out fragmented cinder the next, you get beautifully layered composite cones. Now, if you have that fluid basic lava we talked about, it spreads out into broad, flat giants known as shield volcanoes. Right at the very top of the vent, you'll usually find a funnel-shaped depression called a crater, which, by the way, can fill with water and become a stunning lake. And sometimes, this highly fluid lava doesn't even bother building a mountain. It just pours out of fissures for hundreds of kilometers, creating massive plains called flood basalts. The famous Deccan traps in India are a perfect example of this.
But wait, there is a whole hidden world beneath our feet. Magma that gets trapped and cools inside the crust forms intrusive landforms. Imagine a massive underground gallery of enormous rock sculptures. Down at the very bottom, you have huge dome-shaped batholiths. Closer to the surface, magma might push into horizontal sedimentary rocks and bulge upward into mushroom-shaped laccolith. Or it might pool into shallow saucer shapes called lapiliths. If it settles into the natural waves of folded rock, the anticlines and synclines, we call those faccoliths. And finally, if magma squeezes horizontally between flat rock layers, it forms sills and sheets, while magma that cuts straight up vertically forms massive wall-like dikes. It's like a giant puzzle down there.
That brings us to Section 5, where volcanoes call home. We know what they look like, but if you look at a globe, where exactly are these fiery mountains hanging out? Mapping them out is brilliant because it shows us that volcanoes are definitely not placed randomly. They overlap almost perfectly with the Earth's seismic weak zones, sitting right on the boundaries of moving tectonic plates. Basically, we've got three main neighborhoods. First is the infamous Circum-Pacific Belt, better known as the Ring of Fire, tracing the coasts of the Pacific Ocean. This is home to Mount Fujiyama and the world's highest volcanic mountain, Mount Cotopaxi. Second is the Mid-Continental Belt. This one runs through the Alpine Mountains and the Mediterranean, and it's driven entirely by the massive slow-motion collision of the Eurasian, African, and Indian tectonic plates. Finally, tearing straight down the ocean floor is the Mid-Atlantic Belt. This is a divergent zone where tectonic plates are literally pulling apart from each other, causing massive fissure eruptions and making places like Iceland intensely active. Now, even when a volcano's main eruptive phase is over, the heat definitely remains. We see these post-volcanic phenomena as a volcano's last signs of life. You've got geysers, which are spectacular fountains of superheated water and steam, like you'd see in Yellowstone. You have hot springs, where water sinks just deep enough to be heated gently without exploding back up. These springs, like the ones at Manekaran in India, are incredibly rich in dissolved minerals and are super valued for their medical benefits. And finally, as a volcano's dying breath, you have fumaroles. These are simple vents just quietly exhaling leftover gases and water vapor into the air.
And that leads us to our final chapter, Section 6, Effects, Destruction and Creation. Because to really understand volcanism is to understand a massive paradox.
The destructive power is terrifyingly real. A sudden eruption can bury human habitats and natural wealth in an absolute instant. You've got massive ash fallouts that turn the air poisonous and aggravate acid rain, plus shifting magma that triggers devastating earthquakes. Huge eruptions can even alter the heat balance of the entire Earth, causing temporary climate shifts. But on the flip side, we receive these incredible geological gifts. The lava that burns the land eventually breaks down to heavily enhanced soil productivity, creating literally some of the most fertile farming land on the planet. Water-filled craters become beautiful tourist destinations and vital freshwater sources. And, incredibly importantly for modern society, these volcanic processes act as a primary storehouse, turning up highly valuable metals and mineral resources from deep within the mantle straight to us. So, it's a high-stakes balance, right? We are so drawn to the rich soils, the rare minerals, and the geothermal energy, yet we have to constantly respect the sleeping giants beneath our feet. So I want to leave you with this thought. Knowing this immense, unstoppable power of magma to both instantly destroy and richly create, how does living in the shadow of a dormant volcano shape human civilization today? Think about all those cities built right on the slopes of ancient ash, just waiting for the day the Earth decides to breathe again. Thank you so much for joining me on this explainer. I really hope this helped you visualize the incredible journey of magma. Keep questioning, keep learning, and I'll catch you next time.